All right. 谢谢. Okay. So I think it's about time. Welcome back to DSP. Okay, welcome back to DSP. Okay, so today is our second meeting of my lectures. So today my plan is to wrap up with from the previous lecture. Okay, and then we enter lecture number 2. Okay, lecture number 2 will be an official introduction to what we call DTFT, discrete time Fourier transform, and its properties. And I have uploaded the pre-note. The pre-note should be available on EE class for you to download. So if you haven't done so, please feel free to do it. But otherwise, let's go back to the first lecture, right? Okay, so a bit of a recap. Yeah, what do we have? So we say that we have a continuous time signal. We have a continuous time signal, and we send it through a converter. Okay, and the converter is denoted as C to D. Right? C, of course, stands for continuous. D, strictly speaking, does not stand for digital yet. Okay, strictly speaking, we're talking about continuous time to discrete time, continuous to discrete conversion. And the equation that describes this action is as follows. We have on one end, after the conversion, the result is a sequence of numbers, right? Indexed by n being integers. And the way we handle this, we think about this, is to look at our continuous time signal every once in a while at every integer multiple of t being a period of time, and this period of time is referred to as, is called sampling period. Sampling period. Okay, so the idea is that we have a continuous time signal, and we look at it every so often, t at 2t at 3t, and so on, at integer multiples of t, and we record the value. And this recording may have a unit, right? If the signal itself is in volt, in continuous time, then after sampling, it's still in volt, not digital yet. So strictly speaking, and we'll talk about it later in this course, that strictly speaking, for a signal to become digital, we need to quantize, we need to represent the real numbers by bits, by a binary sequence. Let's say a sequence of 8 bits, a sequence of 16 bits, for example. Okay, so let's agree that we refrain from calling our signal digital if we want to be rigorous about what we say. Okay, and so last time we asked the question, is this sampling action invertible? It is not, because many different signals can map to the same sequence after sampling, right? So here's an example. We have one signal that looks more smooth, the other signal that has more wiggling, more high frequency components. And chances are, just by luck, by chance, the two of them might map to the same sequence of number after sampling, okay? So of course, C to D is not invertible, okay? No. But in practice, still, there is a thing called D to C conversion. Okay, you can talk about discrete to continuous conversion. So what's going on? If C to D is not invertible, why are we still able to talk about D to C? Right? And the reason is because there is a kind of agreement. Okay, so we agree that we want to first consider the bandwidth of a signal. And then we agree that we want to sample at least 2 times faster. That's sort of an agreement among all communication engineers. Let's always sample at least 2 times faster than the bandwidth. Okay, the sampling frequency, or sampling frequency is defined by 1/t. Okay, the inverse 导数, or the reciprocal of t, sampling period, is called a sampling frequency in the unit of hertz. Okay, so we need to sample at least 2 times faster, higher than the highest frequency in the signal. Okay, so last time we started by giving you an example of what if not, a bagged example. What if we don't sample fast enough? right? So you see that when we, in this example, when we don't sample fast enough, the resulting sequence of number may like these red dots, okay? We don't sample so fast, whereas the underlying, the red curve in the background, that's a continuous time signal. So after sampling, if you connect the dots, it looks like a frequency at a much lower frequency. It looks like a signal at a much lower frequency. So there is some kind of confusion right here, okay? When we only look at the samples, it's hard to say why the underlying signal is the high frequency, okay? Is what is shown in red. So this is used as a bad example. What if we don't sample fast enough, okay? But then we went on to talk about if we sample, what if we do sample fast enough? What if our sampling frequency is indeed higher than 2 times the bandwidth? Let's denote the bandwidth as B, okay? So then we are blessed. 我们就有得到祝福. We're blessed with the property that if the signal that we begin with is band limited, and if its bandwidth is indeed finite, I call it B, right? Then it becomes possible to, then we just sample fast enough. Then after sampling, it basically becomes possible to reconstruct the original signal without any ambiguity. We can for sure reconstruct the signal if the signal has a finite bandwidth to begin with, and if we sample fast enough, at least 2 times B, okay? Right, so then it becomes possible to, maybe I shouldn't say uniquely, okay, let's just say reconstruct. Then it becomes possible to reconstruct, at least conceptually, to reconstruct our continuous time signal from its sample, even though it looks like a huge loss of information. Okay? We are only looking at checking the signal at discrete times, but in the end, we were able to, it's possible to reconstruct the original signal in continuous time. Okay? And the criterion that we want to sample fast, as fast as possible, at least 2 times faster than the highest frequency in that signal. Okay? So far, so good. So that's a bit of an overview of what we had last time. Right. So to formulate this mathematically, then we need to introduce another way to look at this action of sampling. So we say, of course, this is true. It is still true that what sampling does is to check the signal, to look at the signal at integer multiple t and call the result is a sequence of numbers. That is still true. Okay, it's nothing wrong about that. Okay, but it turns out that it's more convenient to introduce this function to explain the sampling theorem. Okay, the fact that we recommend sampling at least 2 times faster is a sampling theorem. Okay, to understand what sampling theorem is trying to tell us, to understand that. Turns out that it's easier if we introduce this notion, okay? So last time we introduced a signal called S of t, and it consists of an infinite sequence of impulses. Delta functions are impulse, okay? Delta functions are impulses, and each of them is located at time nt. And we had a review of what delta function is. Usually we write it we draw it as an arrow pointing infinitely to upward. Okay, and the idea is that we all know that delta is 0 elsewhere, but infinity at time 0. But we pretend, we convince, 反正就相信了啊。we come to believe that there's nothing wrong about assuming the integral of delta t is equal to 1. Right? It's a commonly used trick. Okay, so given this trick, now we construct an infinite sequence of impulses, of delta impulses. And the next step I want to convince is recap that then using S of t, we can consider the action of sampling as if we are multiplying the signal, our continuous time signal, with any of them, with S of t. Just equivalently. Why? Because if we multiply our signal with S of t, then the result, of course, is a sequence of impulses, but now their heights are modulated according to the height, the value of our signal. Okay? So the action of sampling is equivalent to multiplying our signal with S of t. Okay, can we agree on that? Yeah, this is just another way of thinking about sampling. Okay? First way is, of course, this definition. Second way, equivalently, you can think of sampling as if we are multiplying our continuous time signal with this S of t. Okay? Then the rest is just derivation. Okay? Then the rest we are going to go to frequency domain. Okay? Go to frequency domain. So the first thing I recommend we should pay attention to is to perform Fourier series expansion of S of t. Okay? And we can do that because note what is Fourier series expansion? For any periodic signal in continuous time, then we can write the signal as a sum of sine or cosine functions, or even better, e to the j omega t, where omegas are the frequency, the angular frequencies are equal to k times 2 pi divided by the period. Okay, any periodic signal, we can perform Fourier series analysis. Okay, and now noting that S of t is indeed periodic, right? Because the impulse, this shape repeats itself. S of t is indeed periodic, just because of that. And just because of that, we can perform Fourier series expansion for this periodic signal. Okay? And the result is, first, we typically just first write it down. Okay? Assume that equality can hold. Okay? Assume that it is possible to express this periodic signal in terms of harmonics. So here we sum over the k being now becomes the frequency index or harmonic index, also integers. And you can express a periodic signal as a summation of complex exponentials. Okay? From now on, I'm going to call this, I often call it this kind of the signal complex exponential. Yeah. That's how I call it, complex exponential. Okay, complex exponential. Emphasizing that the exponent, e to something, that thing is called the exponent, 指数的部分啊。Exponent. The exponent is a complex number. It's a purely imaginary number, actually, e to j something, right? So we all know that perhaps it is also good to make sure that we agree e to the j theta in general equals to cosine theta plus j sine theta. So that's the meaning, okay? And cosine and sine, because cosine and sine are periodic, and so is the e complex exponential functions. Okay, they are periodic, right? And what is the period? The period is t. Okay, right? The period is t. This is the period. T is the period. Okay. So we can express S of t, which is a periodic function, as a sum of complex exponentials, but the only unknowns are all the coefficients are not known yet. Okay? Not known yet. Okay? So there are standard ways to figure out what are the coefficients. Okay? What are coefficients? It turns out that you can make a calculation. Turns out that for this very signal, S of t, the coefficients are all equal, and they all equal to 1 divided by t. Right here. It turns out that this is true. I've done it. You can verify that. All right, so far so good? So far so good. Right? Okay. So now we can finally happily write S of t as summation of complex exponentials and all the coefficients here are equal to 1 over t. Okay. So this is the equality that we can use. That turns out to be pretty useful. Okay, so next I'm going to show you why this is useful. Why this is useful? Remember that we say sampling is nothing but multiplying our signal with S of t. Okay? So how about now, let's just plug this in, just insert, substitute this expression, substitute st by this expression, right? We just figure out that we can do this substitution, okay? We can do this substitution. And whenever and the summation index run go over k, okay? K from minus infinity to infinity, summing over all k, all integers, yeah. Yeah, so this is simple substitution, 只是替那个代入而已, a simple substitution. But then, when we look at this equation, we are now ready to go to the frequency domain. Okay, let's check next. What's new today is that I want to check what's happening, what will happen in the frequency domain. What will happen in the frequency domain? So, maybe let me write one more step. Sometimes I suggest that we may try to put, let's try this. We put our signal into the summation, right? We can do that, right? We'll do this, okay? We'll put this into the summation. So the result becomes xc of t. And also maybe we just push the constant out. We can pull the constant out and put the signal inside the summation, right? Of course, we can do that. Yeah? Yeah, we can do that. And then e to the jk, oh, there is, yeah, e to the jk 2 pi divided by t, big T, small t, right? Everything is still, at least in terms of this formulation, t is still continuous, the small t, little t, is still the continuous time variable, right? Still continuous time variable. Okay, so now, when we consider the Fourier transform of this entire thing, there is a theorem. There is a modulation theorem that we can use. That's pretty convenient here. Okay, it says that whenever we multiply a signal with e to the j certain frequency, okay, so maybe you can even denote this frequency. Now let's denote it a little bit. Let's denote this frequency as, it's too thick. This is a bit too thick. I want to change it, change the width. Strange. Here. Oh, yeah. Because, oh no, this. Sorry about the confusion. So this frequency, k2 pi divided by k times the fundamental frequency. Okay, so this is a frequency, and let's denote it as omega k, right? Let's define omega k as k times 2 pi divided by big T, right? So here is the concept. When we have any signal xc of t and we multiply it with e to the j omega 0 t, okay, in the time domain, then we take the product right here, and then the Fourier transform of xt times e to the j, any frequency, any fixed frequency, or any constant frequency right here, is equal to shifting in the frequency domain. This is modulation. Okay, we modulate our signal, so that our signal becomes a message, and this function here is a carrier. Okay? If you think in that way, this is AM. This is amplitude modulation. We are modulating the carrier with a baseband signal, if you will, even though we don't emphasize this too much. But anyway, mathematically, when you multiply a signal in time with a complex exponential of fixed frequency, then what happens in the frequency domain? What happens in the frequency domain is that the result is equal to x, its spectrum. The spectrum is shifted. Okay, the spectrum is shifted to the right, okay, to the right by omega 0, okay? Yeah. You know what? I kind of just let me put let me modify this. Okay, I want to use big omega instead of lowercase omega. Right? Sorry for the for the change. Okay, big omega. Okay. So, but anyway, for when we multiply our signal, so let's again look at inside here. What we have inside here is multiplication of our signal with the complex exponential. So now, after taking the Fourier transform, the result of this summation. So we know that, therefore, Fourier transform of this x s of t, which is right here, our signal, okay? So after the transformation, we are taking just copying everything from there. I'm just copying everything to this place. And then we know that we can take 1 over t out because Fourier transform is linear. And we can also put Fourier transform inside because it is linear again. So because of linearity, you can do this arrangement, and we're almost there. F x of t times e to the j a certain frequency omega big omega k t, right? Then we know that the result is 1 over t times what? Times, now we apply this relation, okay? Now we apply this relation. Now we're ready to apply this property. Modulation in the time domain, shift in the frequency domain, okay? Shifting the entire spectrum to the right by that amount. So let's finish writing this. Now we still have the summation, but then this result of Fourier transform becomes xc omega shifted by k times 2 pi divided by t, and this k is the summation index. Okay. So let's kind of take a break from here and let's contemplate on this result. Okay. Let's contemplate. 我们来凝视一下这个结果啊。Let's contemplate on this result. Let's contemplate on this result. Okay, and we should have a discussion. Okay, we should have a discussion. So do I have room for drawing? Yeah. Let me maybe cut things smaller. Okay, this can be smaller. Yeah. Smaller. Move here. Okay. Yeah. All right. So now we want to draw a few pictures in the frequency domain. Okay. Yeah. So remember that we assume. Note that we assume we have a signal. Okay, any signal in time, and after taking the Fourier transform, it goes to the frequency domain. It goes to the frequency domain, and let's draw the frequency spectrum. Kind of let's have an illustration of a spectrum. Okay, in general, the spectrum may look any shape, right? But let's for now just represent the spectrum by a triangle. By a triangle. So let's say the spectrum looks like this. Okay, this is our spectrum with a bandwidth. With a bandwidth of b. That's how we talk about the bandwidth of b, right? Or should I say b times 2 pi? Because b is in hertz. If b is in hertz, then 2 pi b is the bandwidth in radian per. This is omega in radian per second. That's the horizontal axis. The unit to our horizontal axis is a radian per second. Okay, 2 pi times the frequency or angular frequency. So this is our baseband. But then, when we multiply with e to the j k times 2 pi divided by t small t, right? Now, this result, the result that we just obtained, okay, the result we just obtained right here is that when we multiply, when we sample the signal, let me just directly go for sampling. There's no need to talk about this more, repeatedly talking about this one. Then, when we sample our signal, the spectrum becomes a summation of the original spectrum, but shifted to the right or to the left, depending on if k is negative or positive. Okay? So in the end, we have infinitely many copies shifted to the right by 2 pi divided by t, or to the left by the same shape, 2 pi divided by t, and so on. We have infinitely many copies of this triangle, which illustrates the original spectrum. But after sampling, what happens in the frequency domain is that now we have additional copies of the spectrum elsewhere in the spectrum, and they are centered at integer multiples of t. Maybe I should, let me do the magic again. It's convenient of using this writing pad. Okay, so I'm kind of not organizing my space very well. So, but let me, move things around so you may guess what I'm about to do. I'm about to, to emphasize that there are infinitely many copies. Let's extend our frequency range a little bit, okay? So of course, at 2 times, that's just toward the negative direction. Toward the negative direction, by 2 times the sampling frequency, now we have minus 4 pi divided by t. There we get a copy of the spectrum as well, okay? And same thing to the positive side. If we just extend our frequency axis, so we can expect that there at 4 pi divided by t, again, we have a copy of the spectrum. Okay? So that's what sampling is giving to us in the frequency domain. Consequently, when we multiply our signal by those impulses, delta impulses, what happens in the frequency domain? What happens in the frequency domain is that we have infinitely many copies on top of each other. This is a summation. Seriously, this is summation. Okay, but this is the case when we sample fast enough. When we sample fast enough, that means that we have enough spacing. Okay, that means we have enough spacing. That means this copy and the next copy are far enough away from each other, so their bandwidth, their spectrum do not overlap. Their spectrums do not overlap. This is good. Okay, so now it should become clearer and clearer why we mean we need to sample at least 2 times higher than the bandwidth. Okay, because the bandwidth is this half, right? The width, that's the bandwidth. So, and there's also this bandwidth, and we need to talk about, assume that our signal is a little bit clearer. So all the spectrums in this course, unless otherwise mentioned, okay, all the spectrums are going to be symmetric, because we assume the signals are real in time, okay. So if you have questions, we can discuss. But know that at least according to my drawing, we have a symmetric spectrum. It's always the case. We can always assume that in reality, so that we need this is basically 2 pi times our sampling frequency. Okay, so it turns out that 2 pi times our sampling frequency needs to be needs to be larger. Need to be larger than this width plus this width. Okay, that's larger than 2 times 2 pi b. That's the criterion. Okay. Therefore, dividing just canceling 2 pi. So the conclusion that therefore, let me write therefore. Therefore, we require, this is a requirement, okay? We require Fs to be greater than 2b so that we don't need to worry about spectrums overlapping, okay? When spectrums don't overlap, then we don't have any trouble, okay? We don't have trouble, okay? And so when I say we don't have trouble, that means when we eventually need to we can recover the original signal by applying a low-pass filter. Okay, this might be too fast. So when they don't overlap, that is this situation. So now we have infinitely copies of the same spectrum elsewhere in the frequency domain. So to recover the original spectrum, we just need to apply a low-pass filter, okay, here. Okay, by applying a low-pass filter, then we just retrieve the middle one, the one in the middle, which is the original spectrum. Right? So just technically, there are ways to discard any extra copies in the frequency domain. This is why we say to summarize, to conclude. This is the requirement or the recommendation. Okay, we require or we recommend. We recommend setting our sampling frequency at least 2 times higher than at least 2 times the bandwidth, so that even after sampling, there will be no overlap between spectral components. And if you ever need to reconstruct the original signal, just apply a low-pass filter and then perform inverse Fourier transform. Right? Applying a low-pass filter and the inverse Fourier transform will give you back the original signal. And we are talking about reconstruction. Okay? There are ways it is possible to reconstruct the original signal. We'll come back to this, okay? At least, but I want to mention to you the notion of low-pass filtering. Okay, use a low-pass filter to just retrieve the middle one, while discarding everything else. After you do that, then we can apply an inverse Fourier transform. We are getting back the original signal, okay, mathematically. But now, to just really understand what goes wrong when the sampling rate is not high enough. Okay, so now let's talk about the situation. So this, what we just talked about is the first situation. Is the first situation. This first situation, when our sampling rate is high enough, then this is what we have. Okay, but what if, let's practice. What if our sampling rate is not high enough? It's not high enough. So let's repeat the thinking process one more time. Let's try to repeat the thinking process one more time. Okay, now I know that I need to draw a long line for the frequency. Okay, a really long line again, big omega, and the unit is radian per second. Okay, really long line, and then assume that still our baseband is in the middle. Okay, at DC, we have this baseband signal, okay, which has a maximum bandwidth of 2 pi b on one side and minus 2 pi b on the other side, okay? So this is our spectrum. The black is the original spectrum, right? But how about after sampling? After sampling, again, we look at this equation, okay? This equation, right? We look at this equation. There is a summation, so using the same equation, we are going to shift the spectrum to the right and to the left by integer multiples of basically a sampling frequency. Okay, and let's now think about having a low sampling rate. Sampling rate is too small. Okay, let's say if the sampling rate is so small. Now, if the sampling rate is so small, if this frequency right here is 2 pi divided by t, okay? And 2 times that, that's 4 pi divided by t, okay? Then what's happening is that we are going to have extra copies, okay? Now, still, similarly, we are going to have extra copies, but now they interfere, they overlap. I'm not drawing a very good figure, you know what I mean. They overlap with each other, with one another, okay? So to the left, symmetrically, we have the same thing here. Let's say if this frequency is minus 2 pi divided by t, and this frequency is minus 4 pi divided by t, just complete drawing, okay? So we have one copy of the spectrum which is going to overlap with our original spectrum, okay? And same thing, similarly, this will happen repeatedly in the frequency domain. Okay? Now they overlap, okay? So now they overlap, they sum up actually. So they overlap, and wherever they overlap, in those frequency regions, they sum up. The spectrums sum up. Because this is simply a summation, okay? They sum up. So you can see that now, wherever they overlap, they sum up, and the result may look like that, okay? This is just a cartoon, okay? Because remember that the spectrums are complex numbers. So you can argue that the exact shape might not be a flat line, but allow me to use this is just an illustration. 这是一个图案说明而已。Okay, so this is just nothing but an illustration. But here we notice that now now the spectrum sums up, okay, and so on. So the resulting spectrum after sampling becomes they lost the original triangular shape, okay? The resulting spectrum now looks like this. The triangular shape is not entirely preserved anymore. It's not preserved anymore. Now the shape looks different. At this frequency region where two copies of a spectrum overlap, right here, and right here. Now the spectral shape is not the same, becomes not the same. They're mixed. They are mixed. They are messed up. They're mixed. 混合起来了. They're added on top of one another. So when they're added on top of one another, then basically there's no way. Okay, there's no way to separate them. There's no way to separate them because Fourier transform really is a unique representation of the signal. So when they're messed up in the frequency domain, they're messed up in the time domain. They're just really, really mixed. Okay, there's no way you can retrieve the original triangular shape spectrum. Or you tell me, do we have a low-pass filter? Will the low-pass filter still work? No. Okay, even if we apply a low-pass filter, even if we try to apply a low-pass filter now, the resulting spectrum is not that beautiful triangle shape anymore. There's going to be distortion, okay, because of the overlap in the frequency domain. Okay, and this is all this useful equation is telling us. Okay, this equation, it tells us a lot. Okay, it tells us after sampling, we have multiple copies of the spectrum, and they might overlap in the frequency domain if the sampling frequency is not higher than 2B. Okay, so far so good. Yeah, is that clear? Okay, so what do we do? So in the end, we require let's always sample fast enough. Okay, right? Let's always sample fast enough. That's kind of simple answer, right? Right. So yeah, so much about the sampling theorem. So now finally coming to a conclusion. Now we can just talk about officially talk about this theorem again. So let's write it down. Okay, let's write it down. So to summarize, what do we have? Suppose that we have a continuous time signal, and its Fourier transform is a spectrum. Okay, and suppose that this is kind of the mathematical way of saying the same thing, saying that suppose that signal is band limited. Okay, so how do we say that? Let's try. We say that suppose that there exists a finite bandwidth, finite frequency omega called n. Okay, suppose there exists a finite omega, finite angular frequency denoted as omega n, finite. Okay, not infinity, such that our spectrum is equal to 0 anywhere at any higher frequency. Yeah, is that clear? This is the way we describe that a signal has a finite bandwidth. 频宽是有限的啊。Suppose that there exists a upper bound such that the spectrum is equal to 0 for any frequency that's higher on both sides, okay, negative or positive. For any frequency higher than this upper bound, the spectrum becomes 0, it vanishes to 0. 消失, vanishes to 0. Okay? That's a way to describe, to talk about a signal which has a finite bandwidth. Right? Yeah. We'll see this more. Then what happens? Then, so what's important is after then. Then we say, then xc of t is uniquely determined. The x is uniquely determined by its samples. And the samples is, again, let's repeat this definition. Samples means xn equals to measuring xc at n times t. Okay? Where n is equal to blah blah minus 2, minus 1, 0, 1, 2. N is all taken at all integers, right? But then xc is uniquely determined by its samples if our sampling frequency that's defined as 2 pi divided by t is greater than 2 times this upper bound. That completes the description of a theorem. Okay? That completes the description of a theorem. Right? Suppose that the signal is band limited. Suppose that it has a finite bandwidth, and above which the spectrum vanishes to 0. Okay? Suppose the signal is indeed band limited, then we can feel free to sample the signal, and we will be able to reconstruct or to find the unique xc of t that correspond to the samples if the sampling frequency is greater than 2 times the upper bound. And that upper bound has a subscript n, right? This subscript n stands for Nyquist. It's probably the name of this scientist, okay? And the theorem is referred to as the Nyquist-Shannon sampling theorem. Lesson, what is the lesson? We want to sample at least 2 times omega n. At least 2 times the sampling, the Nyquist rate. Okay, this upper bound is often referred to as the Nyquist frequency. Nyquist frequency, Nyquist angular frequency. Okay, should be clear. The upper bound of of the frequency. Okay, above which we have no signal. Right. So now, to wrap up this lecture, we have a few remarks. Okay, we have a few remarks. First, as I try to mention briefly, usually we assume xt, our signals are real numbers. Okay, and consequently, for any real number, the spectrum is going to be symmetric around frequency 0. Okay. The magnitude spectrum is going to be symmetric around frequency 0. Right? If we just take the negative sign here, considering the negative frequency, at least the magnitude is going to be the same as the positive frequency for all omega. Okay? And that's why, therefore, I always draw a triangle. Okay? A lot of people like to draw a triangle, because to emphasize that this is a real signal, the spectrum is symmetric. Okay? Yeah. Okay. That's why we draw a symmetric triangle. Okay? Yeah. And next week, we will introduce what if, if indeed we have sufficiently high sampling rate. If indeed the sampling rate is high enough, then how do we actually reconstruct the signal? So we have talked about what I have suggested to you. I suggested to you that we are going to apply a low-pass filter, an ideal one, ideal low-pass filter. How do we reconstruct? The verb is reconstruct. How do we reconstruct the signal from its samples? How exactly should we do it? Okay, and so we'll put that to next week. Okay, so next week, and so today I'm kind of actually running slower than I expect. But any question? So okay, so next week when we come back, then we head to my second lecture. Okay, my second lecture, which will be about an official introduction of a version of Fourier transform, which is called discrete time Fourier transform. Okay, so far I have assumed that you have encountered continuous time Fourier transform. Okay, we have been using it, or even using a shift theorem, right? Modulation in frequency, shift, modulation in time, shift in the frequency. Okay, we have used some properties of continuous time Fourier transform. Next week when we meet, we officially introduce the discrete time Fourier transform. Okay, so thank you for being here. See you next week. See you next Wednesday. Yes. Yeah. Now I have completed. Now I have completed lecture 1. I will upload my writing, the entire writing pad to the web.
Any lecture notes that we can refer to?
No, I suggest referring to the